Okay, this is going to go over the half-life activity, which we did in the fall. It's a review for it here in the spring. So you can read up on the background. The basic idea is that radioactive atoms are going to decay, and they decay until they get to a stable atom. They're going to give off what we call daughter isotopes. Okay, so in this experiment, you received your little cup. It had however many plastic pennies, if you want to call them. They have a head and they have a tail. You basically count out how many you have, you put it in the cup, and you shake it up, place it on the table, and count how many had their heads turned up, and you count how many remain, and you continue this until you get to 0. And so you do this at least 3 times, and then we take the average of it. Okay? And so in the fall, we graphed your data and we looked at it to see what kind of graph we would produce with that. You're welcome to do that again. All right? So just going back over it, the idea is that it is half-lives. So let's say that I start with 50 objects in my cup. After a half-life, then I should have 25 that are still radioactive. I shake it again for my half-life. I end up with 12.5, so it's rounded to 13. Then shake it again. 13 goes to 7. Shake it again. 7 goes to round up to 4. Shake it again. 4 goes to 2. 2 goes to 1, and 1 goes to 0. So theoretically, when I do the activity, it should take me 8 flips to get to stability. So question number 1 is asking for your theoretical number. Then question number 2 is getting into your actual data, your data. So how many times it takes for you to get to 0. And sometimes what happens is you get hung up and it just keeps flipping, and you can't get to flip up to the tails. Question number 3 asks you to do the average. So remember, average is taking trial 1 plus trial 2 plus trial 3 and divide by 3. Question number 4, each flip is equivalent to a half-life. Did your number on the half-lives differ from what you expected? Question number 1. That's dependent upon your interpretation. So look back at question number 1. How does it compare back to question number 1? Then, this is asking you, well, what would happen if you did more trials? And hopefully you understand at this point that if we did more trials, we should get better results and we get closer to the average. Question number 6. So if I do 200 versus 20, same concept. More pennies just means more data, and it should be better averages. 7 is giving you two elements, element X, element Z. Element X, the half-life is 10 years. Element Z is 20 years. So we start with 100 atoms. Both of them have the same amount of atoms. And we want to know how much is left after 20 years. So since element X has a half-life of 10, it takes me 2 half-lives to get there. So here I go, 50 to, that's my first half-life, and then 25 is my second half-life. So I had 25 left after 2 half-lives. For element Z, since my half-life is 20 years, it's going to take 1 half-life, and I end up with 50. Question B, how much of each element is left after 40 years? So now I'm going to go 40 years, or 2 more, or 20 more years. For element X, that means I do 2 more half-lives. And so 25 goes to 12 or 13, depending on how you round it. And then 6 or 7, depending on how you round it. Element Z, 1 half, I go from 50 to 25. C says how many half-lives does it take for each element to decay entirely? Well, I started with 100 atoms. It does not matter if it's 10 or 20 years of half-life. If I'm given enough time, they will both get to the same amount. So, if you do the math on it, it takes 7 to 8 half-lives to get to 0. For element X, that's 70 or 80 years. For element Z, that's 140 to 160 years. Question number 8 and question number 9 You guys can look that up. Okay? That is a wrap up of the half-life activity. Live long and prosper.